Hello, welcome to Analog Electronic Circuits. This is lecture 7 and today I plan to talk about common gate and common drain circuits. So, this is the plan, but let us see how far it goes. So, in the last class we had studied the common source amplifier. The common source amplifier had the source common to the input port as well as the output port, or in other words, if I draw a sketch, this is how it looked like. Remember, this is how the small signal picture looked like for the common source. The source is common to the input port as well as the output port. This is the input port, this is a 2 port network. The input port is between gate and source, the output port is between drain and source. And now of course, the other possibilities are to have the gate common and next the drain common. Okay. So, which one do you want to do first? Let us do the drain common first. Okay. So, the common drain circuit, this is the expectation that there is going to be an input port and then the drain of the MOSFET is going to be the common node. All right, this is the bare bone structure. Of course, you can flip it and draw it, but I like drawing like this. I mean, if you flip it and draw it, it will look like this. The same thing. That is how it will look like. It will look exactly like before, but with source and drain interchanged. But then I prefer the I prefer drawing it in the way that I have drawn in at first with red. The reason being that I like to keep the drain above the source. I do not like the source going above the drain, and I do not like current going from bottom to top, because that is what it looks like in the green circuit. It looks like the current is going from down to up. This is the flow of current, right. I do not like this. So, that is why I like drawing in this fashion. Okay. So, this is the overall topology, but remember, this is not the final circuit, right. This is just the bare bones picture, the small signal incremental picture. This is what it is, bare bones, right, absolutely bare bones. Small signal incremental picture is this drawing. Okay. And of course, you need to develop this drawing into whatever else is required, but all that you have to remember is that the drain terminal is common between the input port and the output port, and that automatically means that the input is going to be at the gate, right, the drain is going to be at ground, small signal ground, and the output is going to be taken from the source, and that is about it. That is all that you need to know, right, and then we can arrange the circuit the way we want. All right. So, once again I am going to go back to the DC operating point circuit. So, this is the circuit that is going to be used to set the DC operating point, fine. And then we want to connect the drain to ground. Okay. So, connecting the drain to ground, one way to do it would be to remove this resistor altogether and short it, and that would be fine because it does not really change DC operating point. All that it does is it increases VDS, which is very nice. Okay. It does not change anything about ID. All right. So, we can modify it automatically. Drain becomes small signal ground, VDD is eventually small signal ground. Okay. And then we have to apply input at the gate. How do we apply the input at the gate? By using a big fat capacitor. And we have to take the output from the source. You have a question? Okay. So, the question is that why don't you apply input at the source and take the output from the gate? Is that reasonable? Taking an output from a gate, can the gate current is always 0. Can you take an output from the gate? This gate does not provide any current, right? This current is 0. Can you take an output from the gate? Is it okay? I mean, you can do it of course, and then you will see that this circuit is useless. Okay. So, we do not apply input at the source and take output from the gate, that is no good, that is just not done. Okay. So, you apply input at the gate, you can take output from the source. All right. In the earlier structure also, we never applied input at the drain and take output from the source from the gate, because it is meaningless. You can't use the gate to drive an output. Okay. So, this is going to be my circuit. This top resistor can be removed, and this is overall the final picture. You have got your DC operating point circuit shown in green, and on top you put the coupling capacitors, so that you can couple the signal in and then decouple the signal out. Fine. And if you want, you can have a load resistor at the output, right. The output is going to drive something, and that can be modeled as a load resistance. Okay. So, this is my circuit, this is the common drain, this is the complete common drain circuit. Fine. And now, what we are going to do is we are going to analyze this. So, the DC operating point is exactly the same as before, there is nothing to analyze, right. You have R1, R2, you find out the ratio of R1, R2, establish the gate voltage, then you can do a KVL and figure out what is ID, or you could just assume that VGS minus VT is approximately 0.2 volt, then you figure out the source voltage, and that automatically gives you the drain current, and then you can go back compute for this drain current what is VGS, what is VGS minus VT, check is it 0.2 volts, oh no, it was not 0.2 volts, it is 0.14 volts, and then readjust, right, make this 0.14 volts plus VT, then compute the drain current, right. Then you find the drain current, check what is VGS minus VT for this drain current, you are going to work out that oh, it was not 0.14, it is 0.142, and you are all set. Okay. So, 1 or 2 iterations at max, and you can figure out what is the exact drain current, you can establish the drain current, couple of iterations is good enough. Okay. And then you say that you have got all the different parameters. You have got the source voltage, you have got the gate voltage, drain voltage is at VDD in this case, because you do not really need the this resistor at the drain, right. In the common source circuit you needed this resistor at the drain, because the drain was driving something. So, at best it would drive an RL, right, at worst. So, in this case you do not need that resistor at all, you can just short it to VDD and you are done. Okay. So, that is the DC operating point. So, VDS is larger in this case. DC operating point having been done, now what do? You short all the big fat capacitors, short circuit all the big fat capacitors, null the static voltage sources. So, VDD is a static voltage source, constant voltage source. So, nullify it, make it 0 volts, which means that this becomes 0 volts, and then redraw, and then if you want you can redraw once again with the small signal model of the MOSFET. So, I recommend redrawing in 2 steps. Okay. In the first step you short the capacitors, null the DC voltage sources, and in the second step show the small signal model of the MOSFET. So, I strongly recommend that you do this redrawing part in 2 steps and not in one single step. There is a reason why. The reason is that a lot of times, once you get a little practice, a lot of times you will not even need to draw it the second time, and drawing it this, I mean the second, actually replacing the small signal model of the MOSFET over here is not necessarily needed. You can do a lot of calculations mentally, right. As an undergraduate student in engineering, you are trying to become an engineer, right, and frankly speaking, engineers, one hallmark of an engineer is to skip a lot of steps. Okay. So, you should try to skip steps. I am not saying that you skip steps in the exam, right. If you skip steps in the exam, that is probably okay, as long as you get the right answer. Not probably okay, it is absolutely okay as long as you get the right answer. But if you do not know how to get the right answer, then do not skip the steps. Okay. Elaborate all the steps clearly and then do it. But if you are confident, and that is what I want you to be, you need some confidence, right. If you want to be confident, then it is a good idea to skip a few steps, to practice skipping a little bit, because that is engineering for you, right. Engineering, you skip a few steps, you do not do everything accurately, right. You are really interested in reaching the as close to possible as close as possible to the final answer in a very short amount of time. Okay. So, my recommendation is, do not plant the small signal model of the MOSFET in the first go itself, right. Redraw once and then redraw a second time if needed. So, right now we will need to do it because we do not know the steps, but later on you will find that you do not need to redraw it the second time. Okay. So, I am going to redraw this with what? What am I going to do? I am going to short circuit these capacitors and I am going to null the voltage source. That is the job that I am going to do. Okay. Now, the technique that we are going to use to analyze this circuit is something that you have learnt in circuit theory, You have learnt about the Thevenin and Norton equivalence, right? Thevenin equivalent and the Norton equivalent. So, in analog electronic circuits, we are going to have a bias. These both of these techniques, the Thevenin equivalent technique and the Norton equivalent technique, they are as good as each other, right? And most of the time they are equally difficult or equally easy to work with. However, in analog electronic circuits, we will strongly prefer using the Norton equivalent. Okay, strongly preferred. This preference is so strong that almost always, okay, as long as you are using a MOSFET, you are going to use the Norton equivalent method. Okay, this is the method that we are going to use to analyze the circuit. Okay, so what do I mean by the Norton equivalent method? So, recollect the Norton equivalent method. You have a box with two wires coming out, okay, connected to a load resistance, right. So, you are going to model the box as a current source which happens to be the short circuit current, right. If I make a connection between these two, there will be a current through this red wire, right, that is the short circuit current. And in shunt with the short circuit current, you will have the equivalent resistance or impedance of this black box. How will you measure the equivalent impedance or resistance of this black box? You are going to null all the voltage sources inside, look in from outside to measure Rn. All right. So, this is the technique we are going to use, and then you are going to apply RL and you are going to solve the circuit. So, this is the Norton equivalent method. This is just for your recap, and this is what we are going to do, right. What we are going to do is to find out the short circuit current that will give me IN. So, basically I am going to replace RS parallel RL with a wire and find IN, that is going to be the short circuit current, right. If you are confused, think of it this way: if I replace RL with a wire, all of IN is going to flow through RL, that will give you the all of IN will flow through that wire, that is going to tell you the direction of the flow of current, right. So, it is important to know the direction. Once I have done that, I know IN, and then the next step is going to be to find out the output impedance. So, I am going to nullify all the input voltage sources, that is V in, and then measure the resistance looking in from the output. So, how do you measure the resistance? We will apply a voltage and see how much current goes in. So, this is the standard technique that we are going to use. This is the Norton equivalent method. All right. So, what is the first step in the Norton equivalent method? The first step, notice that I have not yet redrawn the MOSFET. Okay. I need to replace the MOSFET with its small signal model. I will do it. I just want to elaborate a little bit as to what exactly I want to do before doing it. So, the analysis that I am going to do is I am going to model this box as IN Rn, where IN is some function of V in, right, Rn, and then I am going to apply RS parallel RL over here and compute the voltage V out. That is my plan. This is the plan. Okay. So, let us do it step by step. First, we are going to measure the short circuit current. So, this is my circuit. and you will see how easy this is. Okay, this was the original circuit. So, when I short circuit, I am going to short circuit over here and measure the current going through the short circuit wire. So, that is exactly what I have done, right. I have connected the source back to ground, and now I want to measure the current in the source. What is it? So, I apply V in over here, right. Now, imagine the model, imagine the model inside this MOSFET, right. I am not going to redraw it, but this is just for your imagination. Inside the MOSFET, this is what is there. Okay. You want a GMB also, GMB does not matter, source is to ground, source is connected to ground. Okay. So, that body voltage is not going to play a role, but inside the MOSFET this is what is there. There is a GM VGS and then there is an RDS. And what is VGS? VGS is V in, right, it is appearing across gate and source. So, GM times V in is the current that is flowing over here, and RDS is not really going to carry any current at all, because both sides of RDS are at 0 volts. So, IN is nothing but GM times V in, and you are done, right. So, this is something that you imagine, okay. You do not really have to draw it every time. I have drawn it right now just so that this is the first time we are doing it, but the next time you just think what is inside the MOSFET. This is a GM, there is a VGS, GM times VGS, there is an RDS, and then there is GMB times VBS, right. VBS is 0, so GMB VBS does not matter. RDS has both sides connected to 0 volts, so RDS does not matter. All that matters is GM VGS, and VGS happens to be equal to V in. So, IN is nothing but GM times V in, okay. And we have found out the Norton equivalent current already. So, one job is already done. Now, the next job, what do we have to do? We have to null the voltage source, look in from outside and see how much resistance do we have. So, we have to null this voltage source first, okay. So, when I say null the voltage source, it means make the voltage source equal to 0 volts. So, if I null this voltage source, the voltage source has 0 volts, a short circuit, this R1 parallel R2 is irrelevant. And this is all you have, okay. And now, once again you do not really have to draw it, but let us draw it. So, you want to measure with a multimeter, you want to measure the impedance looking in from that terminal, okay. Or in other words, you apply a voltage of V over here and see how much current goes back inside. So, I am going to apply V and see how much current is going inside the circuit. Fine, this is the plan. Now, there are two or three things inside this MOSFET, okay. The first thing that is there is RDS. If I apply V over here and I have got RDS connected between V and ground, what is the current in RDS? It is V by RDS, okay, or in other words it is V times GDS, that is one current going. Then there is a parallel path, okay. Once again imagine the MOSFET. The MOSFET has RDS, fine, these are the elements inside the MOSFET. So, I have applied a voltage V at the source, I have already found out that the current in RDS is V times GDS. So, this current is already accounted for, done. Next, continue with the same exercise. I have applied V voltage over here. What is VGS? Gate is at ground. If I apply V voltage over here, VGS is minus V, which means GM times V current is going to go upwards. Okay, corresponding to this current source, right. VGS is now minus V. So, all that you can think is that the current source direction flips, which means that GM times V current is now going upwards as opposed to GM VGS going downwards. What about, so we add that on, and then what about here? The body is also at ground, body is always at ground, which means exactly the same thing happens. I have applied V at the source. So, VBS is really minus V, which means GMB times V current is going upwards. So, I have applied a voltage V and I have got a current V times GDS plus GM plus GMB. I have applied a voltage V, I have got a current V times GDS plus GM plus GMB, which means that the impedance looking into this node over here is equal to 1 by so this is your Norton equivalent resistance, fine. Now, what this means is that this entire circuit, this entire box, this entire dashed area, this red area can be modeled as, so let me redraw. Right, this is what we are trying to model. This entire region can be modeled as where I n is nothing but GM V in, R n is nothing but 1 by GM plus GMB plus GDS. Okay. So, that is the model, this is the Norton equivalent model. and therefore, what is the voltage over here? So, I have got a current I n in shunt with R n trying to push current into R s parallel R L. Okay. This is going to be some current sharing, or you could think of, you could try thinking of combining these two resistors. Now, you get R n parallel R s parallel R L, and then I n is pushing current into this. So, the net voltage is going to be I n times, so this voltage, this is V out, is going to be I n times R n in parallel with R s in parallel with R L. Okay. And R n in parallel with R s in parallel with R L means 1 by, okay. So, I n is G m V in, and R n parallel R s parallel R L is 1 by R L becomes G L, R s becomes G s, and R n becomes G n. G n is nothing but so much. Okay. So, this happens to be your voltage gain V out by, okay, V out by V in. Fine. So, the voltage gain is equal to G m by G m plus G m b plus G d s plus G s plus G L, and naturally if you look at this fraction, then naturally this is always strictly less than 1. Why? Because you have got G m in the numerator and G m plus other things in the denominator. Any questions? You have a question? Yeah. What is the utility of the circuit? Yeah. So, what use is a circuit that has a gain less than 1, right? You want voltage gain, you think, do you think that voltage gain is everything? What about current? What about current? Current also can have some gain, loss, etc., right. So, voltage gain is not necessarily everything. Okay. Power gain is what matters. At the end of the day, are you amplifying power or not? Amplifying power means you are drawing power from the voltage source, from the DC voltage source of course, but the signal power, is it getting amplified or not? That is the bigger question than voltage gain. Okay. So, let us see if we are amplifying power or not, and the answer will be yes, you are actually increasing the power. Even though the voltage is less, the current is going to be more, and therefore, the power is going to actually get amplified, hopefully. Let us check, right. So, power gain is what matters the most, not voltage gain. Okay. So, this circuit is very useful, do not worry. Even though the gain is less than 1, it looks like it is completely useless because the voltage gain is smaller than 1, but very soon you are going to figure out that this circuit is very useful. Okay. So, first of all, let us try to understand power gain. Okay. So, do you know the maximum power transfer theorem? What is the maximum power transfer theorem? If I have got a voltage source V in series with a resistance R s, then the maximum power will be transferred to a load R L if R L is equal to R s. This is the maximum power transfer theorem. If you work it with impedances as opposed to resistances, then ZL has to be equal to conjugate of ZS. So, ZL should be equal to ZS star. All right. This is the statement of the maximum power transfer theorem. Now, the converse is not true. So, you can't state this maximum power transfer theorem in the other way. For example, you can't write R s equal to R L. This is wrong. R L is equal to R s, not R s is equal to R L. You want me to clarify? If R L is equal to R s, why is R s not equal to R L? Okay. Yeah. So, this is a technicality, and yes, this is something very important. You cannot write R s is equal to R L, and I will state why. So, here the unknown is R L, the unknown is not R s. Okay. The statement of maximum power transfer theorem is as follows. If I have a voltage source V in series with a resistance R s or an impedance Z s, then maximum power is transferred to a load Z L if Z L is equal to Z s star. It is not if I have a V in over here and R s over here, maximum power is transferred to Z L if Z s is equal to Z L star. No. Okay. Why not? Because maximum power will be transferred into Z L if Z s is equal to 0. If you have any flexibility in choosing the value of the source resistance, then the source resistance should be equal to 0. Okay, and that will give you maximum power, right. For example, in this case, if R L is equal to R s, then what do you get? So, let us say yeah, this is R s. So, this voltage becomes V in by 2, right, and V squared by V in by 2 whole squared by R L will give you the power delivered to R L. So, that is V in squared by 4 R L is the power delivered to R L. But if you could choose the value of V in squared by 4 R s is the value of the power delivered to R L. Okay. If you can choose instead the value of R s, then I would suggest make R s equal to 0. Okay. If I make R s is equal to 0, then all of V in appears across R L. The factor of 4 goes away. Now, I have V in squared by R L. You see what I mean? So, that is why R s is equal to R L is incorrect. You should not write it this way, you have to write it the opposite way, R L is equal to R s. So, anyway, so this is the maximum power transfer theorem, this is a diversion. Okay. But what we say is that the available power from a voltage source is V in squared by 4 R s. This is the maximum power that you can deliver to a load R L, right. You have flexibility in choosing the value of R L, but R s exists, right. R s is fixed, and the maximum power that you can deliver to a load is V in squared by 4 R s. This is called the available power from any voltage source. All right. So, this is the definition. Now, think of the following, you have got a sensor. This sensor could be some microphone pickup, this microphone pickup. Okay. This microphone pickup has a fixed source resistance, suppose. In that case, the available power from this microphone pickup is V in squared by 4 R s. This is the available power. Power more than this cannot be taken out of the microphone. V in squared by 4 R s is the available power. A power more than this value cannot be drawn from this microphone at all. Done? Now, I am placing the amplifier in between and I am delivering power to a load, to an arbitrary load, all right. So, then, so suppose this is your common drain circuit. Now, imagine the following. Suppose in your common drain circuit, this voltage source comes with a source resistance. Now, what is going to happen? Forget about R1 parallel R2, it is just annoying. Okay. Let us forget about it for the time being. Suppose imagine R1 and R2 are so high that they are mega ohms. R1 and R2 can be in mega ohms, right, tens of mega ohms, whatever you want. R1 parallel R2 do not matter, okay, they are so high that they are not in the circuit. This is your RS. What changes over here? Does the Norton equivalent current change? Does IN calculation change? Forget R1 parallel R2, right, imagine it is not there, and now I am saying add in, throw in an RS over here. Okay. Does the Norton equivalent current calculation change? There is no current going into the gate, this current is 0. So, V in is still, so VGS is still equal to V in, which means IN is still going to become GM times V in. So, it is still the same. Okay. Impedance calculation, Norton equivalent impedance calculation. I am now going to have a resistance over here called RS. Anything significant going to happen? The current in RS is anyway 0, right, because there is no current in the gate, which means that the gate is still at ground potential, okay, which means all the earlier computation, this particular one remains exactly the same as before. So, Rn continues to be exactly the same as before. So, the Norton equivalent calculation has no change whatsoever. So, I still have exactly the same Norton equivalent over here, right, IN remains the same, Rn remains the same, V out by V in remains the same. Okay. No matter what the value of this source impedance is, what the source impedance is does not matter, it could be 1 mega ohm for example, right, it could be fairly large, the Norton equivalent remains exactly the same. So, the voltage gain remains exactly the same, correct. Do you see what I am driving at? I am driving at the following, that the available power from this voltage source was very, very low. Okay. So, the available power from here is V in squared by 4 RS, but what you got over here, the voltage over here is V in times that voltage gain, which is GM by GM plus GMB plus GDS plus GS plus GL. Correct, that is the voltage V out, and this is GL. Okay. So, the power delivered to GL is this voltage squared times GL, correct, V voltage squared by resistance voltage squared times conductance. So, the power delivered is V in squared times G L times some fraction which is less than 1. How much less than 1 is it? GDS is very small compared to GM. Compared to GM, GDS is very small. GMB is also a fraction of GM. Typically, the fraction is of the order of 1/3 or 1/4, something like that. So, for example, if GM is 1 unit, or let us say GM is 4 units, this is 4, this would be 1, 5, GDS is nothing, right, or 0.1 or something like that. So, 5.1, and GS and GL can be some quantities, which means that the overall voltage gain is something less than about 0.8 or so. This fraction is 0.8 or so. So, 0.8 the whole squared is what I have over here, 0.8 squared times GL times V in squared is the power delivered. The available power from the source is V in squared by 4 RS. So, what is the gain in terms of power? Remember, this RS is the source resistance, not 1 by GS, this is something else. So, the voltage gain is therefore V in squared cancel, the power gain, this quantity times 4 RS, and RS, the source resistance, can be anything, can be very large, which means that potentially this circuit has very high power gain. So, this is an amplifier in its own right, just not a voltage amplifier. The voltage gets attenuated, right, the voltage gain is something less than 0.8 or so, right, but the power still gets amplified, and that is fantastic because it is an amplifier. So, this particular circuit has many names. It is the common drain circuit, but a lot of people call it differently. So, some people call it a voltage follower, because the voltage at the source follows the voltage at the gate to some extent, 0.8 times the voltage at the gate. So, it is also called a voltage follower. It is also called a buffer, because now it can drive, this circuit can drive from a very weak drive, you have power gain, right. So, the input source V in might not have had any available power, it would not have been able to drive a load, but this circuit can drive a load. So, it is called a buffer. So, these are all the different names, one is a voltage follower, one is a buffer, and of course, this is actually the common drain circuit. A lot of times what people try to do is to improve the voltage gain of the circuit. So, right now the voltage gain of the circuit is about 0.8 or so, and one of the reasons why it is 0.8 or so is because of the presence of GMB. So, this GMB over here brings it down. So, if for example, GM is 4 units, GMB is going to be 1 unit. So, this ratio is going to be 4 by 5. All right. So, to improve this, what they try to do is to make sure that VBS is equal to 0. But how can you do that? How can you make VBS equal to 0 when the source is moving, right? The source has got to be moving. So, one way to do that is to make B also move along with the source. So, they connect B to S, and this is a very risky business, right. Connecting B to S in an NMOS device is very risky, because the body of the NMOS is a shared body, it is a platform on which all the other NMOS devices reside, right, it is a common body. So, a lot of times what is done is a PMOS is used, and every PMOS device has its own body, it comes in its own well. A PMOS device comes inside an N well. So, normally what happens is that you have silicon, right, and the silicon is doped, lightly doped with P. This is the silicon wafer, and then all the devices have to be made on this wafer. So, the starting material is P type doped silicon, lightly P type doped silicon. This is the starting material. Now, when you make NMOS devices, this is fantastic because you just implant N plus and make the gate. So, this is an NMOS device, right, but for a PMOS device you need an N type body. So, what they do is they make a little well over here which is called the N well, and inside the N well they make the PMOS device. Okay. So, every PMOS device can be made in a different N well, whereas all the NMOS devices have to reside on the same silicon substrate. Okay. So, if I say that no, I will connect the body of the NMOS device to the source, then you are taking a big risk, right. You are actually connecting the body of all the other NMOS devices to some source, and that is not a good idea, right. If you are going to take a risk with one device, not with all the devices on the same substrate. Okay. So, in that sense you are never really going to connect the body of the NMOS to the source. However, if you are dealing with one PMOS device, one solo PMOS device inside an N well, then you can take that risk. You can say that okay, I will take this body of this particular N well and connect it to the source, and that way you will be able to avoid the effect of GMB, right, because now body and source will be at the same potential, which means this GMB factor is not going to come in, which means now Rn will only be GDS plus GM, and therefore, that will mean that you will have 4 units on top, 4 units in the bottom, right. This will be let us say 0.1 unit. So, 4.1. So, it is now 4 by 4.1 plus GS plus GL, we do not know what those are. Okay. So, the gain can be substantially improved if you use a PMOS device with body and source connected. Okay. Let us stop here. We started with the plan that we will do both common source, common drain and common gate amplifiers, but we managed to do only the common drain circuit, the common drain amplifier. It is not a voltage amplifier, it is more like a power amplifier, right, and it is also called the buffer circuit. We saw the interaction of the body, right. This is the first time the body actually shows up and plays an active role in your circuit analysis. We also saw how to sometimes you might be able to mitigate the body effect by connecting the body to the source externally, right, and that you can do only in case of a PMOS, not in an NMOS. Let us close with this. The common drain circuit is has a gain slightly less than 1 voltage gain, but power gain is a different matter altogether. It can have very large power gain even though the voltage gain is low. All right. So, in the next class we will continue with the common gate amplifier. Thank you.